Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is an example of a vector space where the example is a little bit odd. What's a vector space? A vector space is a non-empty set, and we're assuming that we have addition. If you take two elements of V and add them, you get another element of V, and that addition has properties: commutativity, x plus y is y plus x, associativity, x plus y plus z is x plus y plus z. There's a zero, a vector that when you add it to other things, nothing happens. Every element has a negative. We also have scalar multiplication, and that scalar multiplication follows certain rules. I have a whole video on vector spaces where I go into the definition in some detail. We have an addition and scalar multiplication, and they follow certain properties. A vector space is an abstract object. If you have a non-empty set together with an addition and scalar multiplication that follow these properties, then V is a vector space over R. The over R means that the scalars are real numbers. Elements of V are called vectors, and elements of R are the scalars. I have many videos on particular examples. Rn and tuples are an example of a vector space. Infinite sequences, polynomials with real coefficients, polynomials of degree less than or equal to n with real coefficients, n by m matrices with real entries, functions from R to R, functions from any set to R. These are all examples of vector spaces. In fact, complex numbers themselves are also an example of a vector space. For every one of these things, I have separate videos with more detail showing you how they're vector spaces. Here, I want to have an unusual addition and scalar multiplication where we actually have to check every one of those axioms. The elements of this set, V, are the same as elements in R2. They're pairs of numbers, A, B, where A and B are real numbers. But the addition and scalar multiplication are not the normal ones. And because of that, I'm going to use plus with a circle and at times with a circle to denote this addition and scalar multiplication, and use plus and dot for the usual addition and scalar multiplication of numbers. The way the addition is defined is this. If you take A1, B1, and A2, B2, usually in R2, the way you would add them, you would get A1 plus A2 and then B1 plus B2. But here you don't do that. You get A1 plus A2 plus 1, and B1 plus B2 minus 2. You add 1 to the x coordinate and subtract 2 in the y coordinate. This is a strange addition. It's not the usual addition. And the scalar multiplication is also weird. So alpha, the scalar alpha times AB, instead of alpha A, alpha B, which is what you would normally do, is alpha A plus alpha minus 1, and alpha B minus 2 alpha plus 2. These are my definitions. And for example, if you want to add 1, 3, 2, 2, 5, you don't get 3 8s as you might have expected, you get 4, 6. And if you multiply 3 by 1, 3, if you follow that rule, you will get 5, 5. And the question is is this legitimate? Can I have this addition and scalar multiplication? The answer is yes, as long as the rules are followed. But we have to check the rules. That's the same as asking, is V together with these weird operations a vector space over R? Over R, again, means the scalars are real numbers. That part is not in contest. The question is are the addition and scalar multiplication legit? So V is closed under addition and scalar multiplication. What that means is that if you take two elements and add them according to this rule, you get something in V, and when you multiply it by a scalar, you also get something in V, but it's not clear that the rules are followed. We have to check all those axioms of a vector space to make sure every one of them is satisfied, and that's what we're going to do. Addition is defined by this rule, and the first thing we have to check is x plus y the same as y plus x. Now, x and y, each one of them is a pair of numbers, and the plus is this new plus. So I have to see if this new plus is commutative. I take two elements and I'm asking, is x plus y is the same as y plus x? The proof of the pudding is in the eating. I'm going to add them into both ways and see if I get the same thing or not. If I add in one way, I get that. And if I add the other way, I get the same thing. A1 plus A2 plus 1 is the same number as A2 plus A1 plus 1 because these are normal addition. And the same with B1 plus B2 minus 2 and B2 plus B1 minus 2. So when I add these, the order does not matter, and I have checked my first axiom. The second one is associativity. Is x plus y plus z the same as x plus y plus z? And again, the plus is the O plus, the plus with a circle on it. First, I find A1P1 plus A2B2, then add that to A3B3. First, I add these two, and so I add a 1 in the first coordinate and minus 2 in the second coordinate. Then I add it to the third one, and I get this. When I combine it, I get A1 plus A2 plus a 3 plus 2, B1 plus B2 plus B3 minus 4. I'm just adding a 1 to the first coordinate, subtracting a 2 in the second coordinate every time I do this addition. And so when I do it the other way, I'm going to get the same thing. I do have associativity. Is there a zero vector? We might say that maybe 0, 0, the guy who usually plays the role of 0, maybe that guy is the zero vector. But we add AB to 0, 0, we don't get AB back. So 0, 0 is not the zero vector. The project might be doomed already. We might not have a vector space. But minus 1, 2 actually is the zero vector. That's a very weird zero vector, but it is. How do I know? This guy's raising his hand and saying, I'm the zero vector. Don't look at 0, 0. It's me, not that guy. How do we check? We have to add it to other things. If you take AB and add it to minus 1, 2, according to our rule, you get A minus 1 plus 1, and then B plus 2 minus 2. And so you get AB back again. And so that is the zero vector. Does every vector have an additive inverse? Remember, for every vector, there got to be an NAB that if you add them together, you get the zero vector. And remember, the zero vector is minus 1, 2, not 0, 0. If X is AB, then is there a minus X? That's the question. Can you say if X is AB, minus X better be minus A minus B? That's not true, because if you take AB and minus A minus B and add them, you get 1 minus 2, which is similar to minus 1, 2, but it's not minus 1, 2. It's not the zero vector. And so minus A minus B is not the same as minus AB in this world. If minus AB is the thing that when you add to AB, you get 0, that's not minus A minus B. But minus AB, the thing that you add to AB to get 0, is actually minus A minus 2 minus B plus 4. How do I know if that's true? I know it's true if it satisfies the property. What happens if I add AB to this guy who's claiming to be minus AB? And if I follow the rules, I see that I get the zero vector. I get minus 1, 2. I get 0, so this must be minus AB. And I do have additive inverses. Now for scalar multiplication, that was the way addition was defined, and this is the way scalar multiplication is defined. I take two elements, and alpha is a real number, and the question is that is alpha x plus y the same as alpha x plus alpha y? I do both of those things. Alpha times x plus y, x is a1 b1 and y is a2 b2. So first I have to add these according to my rule. Then I use my rule again and multiply by the scalar alpha, and I get this mess. If I combine everything, I get alpha a1 plus alpha a2 plus 2 alpha minus 1, alpha b1 plus alpha b2 minus 4 alpha plus 2. That just doesn't seem to be a reasonable thing at all. But if I find the other thing, which is alpha x plus alpha y, so this is alpha times a1 b1 plus alpha times a2 b2, then I have to use my scalar multiplication rule and my addition rule to add them. I will get the same thing. And so this axiom holds. The point is that because this is not a usual addition and scalar multiplication, we actually have to go through every step and make sure that all of these things match. The next one is alpha plus beta x, the same as alpha x plus beta x. Again, addition and scalar multiplication are defined like this. I take an x, which is AB, and the question is that is alpha plus beta times x, where alpha and beta are real numbers, the same as alpha x plus beta x. What's alpha plus beta times AB? I use my rule for a scalar multiplication, except the scalar is alpha plus beta. So I get alpha plus beta times A plus alpha plus beta minus 1. This was that extra stuff that this rule threw in. And then I do the same thing for the second one. And I multiply those out. If I do the other one, alpha times AB, and then beta times AB, and then add them, first I have to multiply by scalars, then I use my addition rule, and I will get the same thing. You have to simplify things a little bit to see that you get the same thing. Now I know that this rule is checked. Two more left. Alpha times beta x, is that the same as alpha beta times x? Alpha times AB, defined in this way. Now, x is again AB, is one element of the supposed vector space, and alpha beta are real numbers. And the question is that, is alpha times beta x the same as alpha beta times x? I find alpha times beta times AB. First, use scalar multiplication rule to find this, and then use the scalar multiplication rule again to multiply alpha by that. I get a big mess like this, but things like minus alpha plus alpha cancel. I get this one. If I look at it, that's the same as multiplying AB by the scalar alpha beta. And again, you should be surprised that this is working. This is odd that this weird addition and scalar multiplication is working according to rules. Our final rule is that if you take the scalar 1 and multiply it by x, you get x. You actually have to check that. So if you take 1 multiplied by AB, you just don't get A, you get A plus 1 minus 1, and those cancel. Here you have minus 2 alpha plus 2, and if alpha is 1, those cancel again, and you get AB back, and you have that rule also our point is that if you've defined this weird addition and scalar multiplication, then you do get a vector space over R. Now, how do I think about that? This is a vector space over R. That's what we proved. But where do these come from? This seems just like a very strange thing. And I want to give you a little bit of intuition about that. Think you're living in the usual R2 with the usual addition. When you add two things, you add them component-wise. If you multiply by a scalar, you take the scalar and multiply by both things. But you put these other axes, 1 unit to the right and 2 units down, this blue axis. All the operations are done in the black axis, in the original axis, but you're going to report them in the blue axis. For example, what's 1, 3 plus 2, 5? 1, 3, and 2, 5 are reported to you in the coordinates of the blue axis. 1, 3 in the old axis is really 2, 1. And 2, 5 in the old axis is really 3, 3. In the old axis, 2, 1 plus 3, 3 is 5, 4. That's just a normal way of adding it. But you're not reporting it in the old axis. You've got to go back to the blue axis and you get 4, 6. And that's how 1, 3 plus 2, 5 ends up being 4, 6. It's that we are sitting in a different axis, but doing operations in the old axes. This is the end of this lecture. Like my video if you liked it. Subscribe to my videos if you want to be subjected to more undergraduate math videos on your feed. Keep hydrated at all times.